Tonight we're very lucky to have Jennifer Maas, who is, as an exception to this, our rule, not a SLAC staff member, but she's certainly a good friend of a lot of people here. She got her PhD from Cornell in inorganic chemistry. Actually, Cornell is another place in the US where they have a synchrotron. And in her graduate work, she became a fan of synchrotrons. And the application that she made of this was to take her inorganic chemistry and go to work as a curator at an art museum, the art museum of the DuPont family in Delaware, the Winterthur Museum. And she's really one of the experts in basically how the chemistry of painting conservation and what happens to paintings over the centuries in which a masterpiece has to survive. So we're very lucky to have her come here tonight to talk about this particular mystery of the yellows of the post-impressionist period. I should also say that Jennifer is running a symposium here at SLAC. There's a big meeting going on of all of the synchrotron users. And Jennifer is taking that opportunity to run a little symposium on art conservation and chemistry for the real experts. But you guys are not the real experts, but nevertheless, it's a fascinating subject, and we're happy to have her here to talk about it. So please welcome Jennifer Maas.
Thank you so much, Michael. I'm delighted to be here, and I'm delighted to have the opportunity to share some of these absolutely phenomenal paintings with you. And unfortunately, we're going to learn a somewhat sad story about these paintings, that they are, in fact, changing color as they age, but we're going to look at ways that we can deal with this phenomenon. But first, I want to take a step back and think about why would anyone spend their career doing the scientific analysis of paintings? It seems like such a strange thing to do with one's life. Well, there's many different things that you can learn about an object of art by doing scientific study of the work. And the first example that I'm giving here is authenticity. If you're an average citizen of Palo Alto and you're about to go out and spend $170 million on your next Van Gogh, for example, then you might want to make sure that it hadn't been made in someone's garage last month. And doing scientific analysis of the pigments can help you determine whether or not that's the case. We also work on identifying previous restorations in paintings, and a lot of people don't know this, but it's estimated that when you go to an art museum, about 80% of what you see is the work of the artists, and about 20% of what you see is the work of the restorers and conservators who have repaired the works over time. And often it's only with scientific analysis that you can tell the difference between what's original and what components are replaced. Then we also look into technology of manufacture, what materials and techniques artists will use in order to create images, and this has spawned an entire new field of art history called technical art history. And then I put a star here next to degradation mechanisms, because we feel that one of the most important ways that we can use science to study art is to understand all the physical and chemical changes that it's undergoing as it reacts with its environment. Only by understanding the changes that the works are going through can we recommend proper display and storage conditions for these objects in order to preserve them for future generations. And all of this work is done under the code of ethics of the American Institute of Conservation, which challenges us to do our work either totally non-destructively, so without taking a sample from the object at all, and of course we don't want to take any samples from these priceless objects, or minimally destructively. And so typically when we take a sample from an object of art, it's on the order of a microgram. That's a millionth of a gram. And the largest sample we would ever take from an object of art is a milligram. And I typically say a milligram is about the size of a period at the end of a Times New Roman 10-point sentence. And all of this work is done in the context of the field of art conservation. Art conservation is made up of art conservators, the people that actually do the restoration of the objects of art, and then scientists from a number of different disciplines, including chemists and physicists and materials engineers predominantly, but also geologists and biologists as well. And so together you can think of all of us as doctors of our global cultural heritage, where the scientists are really focused on the preventive care of the objects and also the diagnosis if anything starts to go wrong, and the conservators are responsible for the treatment. And we do this work not 9 to 5, this is a 24/7 job because we are so passionate about art that we could not possibly imagine doing anything else with our career. And that if we could take, for example, this painting, the portrait of Adele Bloch-Bauer by Gustav Klimt, which is just over 100 years old, and allow her and her contemporaries to live for the next 100 years and the next 100 years for future generations, then that would be a career exceedingly well spent. We also have to acknowledge that there is a very large bottom line in this business. And so the Neue Gallery in New York City, for example, paid $135 million for this particular painting. And so you can imagine if the paint started to change color or flake off, which thank God it's not, then the chemists, the physicists, and the materials engineers get called in rather quickly, along, of course, with the art conservators. Okay, so before we can talk about paint degradation, I wanted to do a little bit of explaining about what paint actually is. And you might think, wow, I totally already know what paint is. And I thought I knew what paint was too before I started working in this field, and I realized that I really didn't actually know what it was. So just bear with me for a moment. Paint is made up of pigment. That's the colored stuff. Usually it's a mineral such as the ultramarine blue, this beautiful bright blue that I'm showing here, which is typically used to make the Virgin Mary's robe in medieval painting. Or it's a man-made compound such as Prussian blue, this dark blue that I'm showing here. And it's held together by a binder or a medium. In the case of oil paint, that's going to be some type of oil that's going to dry when it's exposed to air. It's going to oxidize and form a solid. And so linseed oil is typically used, but walnut oil and poppy seed oil were also used. Poppy seed oil was particularly popular in the skies of paintings because it was known not to turn yellow. And so you don't want your sky turning green over time. And so poppy seed oil was good for that. Watercolor is an example of a misnomer. Actually, the binding medium for watercolor is gum, not water, and it's typically gum arabic, but it can be some more exotic types of plant gums like cherry gum. But it turns out that these are actually minor components of the paint, and that the major component of paint is actually an inert filler, something like chalk or gypsum. And this is really the paint manufacturer trying to maximize their profit by using the largest amount of the most inexpensive component possible and the smallest amount of the colored pigments, the most expensive components. So this is a cartoon of what a paint really looks like. Most of what you're seeing is the white filler material, and then you've got the occasional pigment particles and the binder that holds it all together. Now, when we're studying a painting and we need to take a sample, then what we do is use a small scalpel, like the type of scalpel you would use for eye surgery, to take a tiny flake of paint. We mount it up in polyester resin and polish it until you can see the paint layers end on. And that's what's shown here, is a side-on view of the paint layers or cross-sectional view. So it's just like when you cut into a slice of cake and the layer structure is revealed. And so we see the same thing here. There's actually 3 paint layers here, this kind of peach one at the bottom, then the gray one, and then a third pinkish one at the top. And you can see that most of the paint is actually made up of that white inert filler. And you can also see the weave of the canvas here, although typically we don't take a sample of the canvas. I also wanted to point out here that this painting is not varnished, and that's very characteristic of the work of the post-impressionists and the early modernists. They really wanted to break with the academic art of the 19th century, and they wanted to do something really new and different. And so they didn't want the smooth, polished surfaces of the 19th century that a varnish surface would create. So instead, they wanted their philosophy was that matte was modern. They didn't want any varnish on the surface of their paintings, although sometimes dealers would varnish them later on. Okay, so what happens when paint dries? Before you all go stampeding for the exit, it turns out that it's actually fascinating what happens when paint dries, and it's actually pretty fascinating what happens after paint dries as well. So an oil paint is made up of triglyceride, just that stuff that the doctor is always telling us not to eat so much of. And I like to have pastries on just about every one of my slides, and so that's a good source of triglycerides down there. A triglyceride is made up of a long chain of fatty acids, and when those fatty acids react with oxygen, they polymerize and they form a solid, but they're actually pulling up so much oxygen from the air that you can actually measure an increase in weight as the oil paint dries because it's oxidizing so rapidly during that process. And so you might think, after paint dries, well, then you're done. If you look at a painting on the wall, nothing's happening, nothing's changing, right? In fact, there's all kinds of chemistry going on in a painting, even after the paint has quote unquote dried. And what we see happening is that the oil binder continues to react with the water in the atmosphere, undergoing a process called hydrolysis, in which fatty acids are released. And the easiest way to explain this is, have any of you ever gone into your cupboard and grabbed a chocolate bar that's been in there for a few months, and you unwrap it and it's got kind of this white dusty material on the surface of the chocolate? That's actually fatty acid bloom from the cocoa butter coming to the surface of the chocolate, and just the same thing happens with oil paintings. The fatty acids will actually migrate to the surface of the oil paint. But in addition to the binder reacting, the pigments are going to be reacting as well. And so pigments, unfortunately, react with water, with the relative humidity of the environment. They react with visible light and also ultraviolet light. They react with sulfur dioxide in urban environments. They react with carbon dioxide and oxygen, and they even react with each other. So the first system that I want to focus on is the degradation of yellow paints in works by Vincent Van Gogh. And we're looking at, of course, his famous Sunflower series here. And so he did several versions of this image. This one is at the National Gallery of Art, and then we have this one at the Neue Pinakothek in Munich. And then this one is in Amsterdam, and we have one in Tokyo as well. And you get the sense that the shades of yellow are quite different between the 4 different versions of the painting. And in fact, when you compare them side by side, the differences are really quite dramatic. And so what we really want to know about these works is, are they the original colors that Van Gogh intended them to be? And in order to answer that question, we have to know what yellow pigments would have been available to Van Gogh in the 1880s and do elemental and molecular analysis of his painting to figure out what pigments are present. And in particular of concern is the darker yellow shades that we see here. Is this something intentional, or is it a result of surface soil that's present on the painting, maybe because of a dirty varnish? Or perhaps is it the result of the paint degrading over time? And you can imagine there are tremendous art historical implications if this painting originally was supposed to have looked like this one. And there's also tremendous preservation implications as well, in terms of, if this is something that's happening over the course of time, we want to make sure that the other 3 paintings don't all wind up brown like this one. So what is the context of this research? Why are we so worried about these paintings changing color? Well, it turns out that in the last 10 years, we found out that the works of the Impressionist, the post-impressionist, and the early modern masters are not as stable as we thought they were, that after just about 100 years since they were first made, the colors are starting to change dramatically, and the 3 really bad actors happen to all be yellow pigments, and the worst ones are chrome yellow, zinc yellow, and cadmium yellow. And I have pictures here of the jars as they sit in my lab, and you can't really get a good sense of the different shades of yellow, and so I have these mid-century modern kinetic sculpture to give you an idea of what these yellows actually look like. And so you really do get the sense that we have this bright lemony yellow for chrome yellow. This is zinc yellow. It's kind of an acidy, almost greenish yellow. I'm embarrassed to say I actually owned this car. And this is cadmium yellow. It's a nice, warm, orangey yellow. And so in the case of Van Gogh, he was very fond of using chrome yellow. And in the landscape that we see here, the bright and lemony chrome yellow is changing color. It's actually turning brown over time. And so this is the current appearance of the painting shown here in the 2011 image. And because we know the hue, value, and chroma of the chrome yellow pigment, we know that originally Van Gogh intended the painting to look like this. So this is a digital reconstruction of what the painting originally looked like. And then we can also go the other way and do a digital projection into the future and think that perhaps in 2050, this reaction is going to continue, and we're going to have a painting that looks something like this. Now, in order to stop that from happening, we have to think, what is the reaction that's going on here? Is it a reaction, for example, with ambient light or with oxygen in the air or with sulfur dioxide in the environment, even carbon dioxide, or even with surrounding pigments? Until we answer that question, we can't take the steps necessary to preserve this painting for the future. And we also have to ask a question that we often ask in conservation, which is this inherent vice? And we probably all know what inherent vice means, right? Well, actually, it turns out that in conservation, we use this term in a different way than you would use it in everyday life. Inherent vice in art conservation means a material that's ephemeral. It was never meant to last. And probably the best example that I could think of inherent vice is masking tape. If you use masking tape to seal up an envelope, for example, even after a matter of 6 weeks or a couple months, it starts to turn brown, it starts to lose its adhesive properties. So it's a material that you would never want to find in an object of art because it was never meant to last. And we really have to ask this question of Van Gogh because unfortunately he was infamous for using pigments that had inherent vice. And the most important one of these pigments is a red pigment called geranium lake. And the best example of this is seen in this fabulous work from the Van Gogh Museum called The Bedroom. And Van Gogh was very passionate about this work, and he wrote to his brother Theo about this work, and he noted, sadly, everything depends on color. The walls are pale violet. And if you look at it, they're not. They're cornflower blue. So what's going on here? Well, it turns out that he used geranium lake in the walls in order to get that violet color. And geranium lake is made with a bright red dye that's called eosin. And even over a matter of months, eosin fades irreversibly to white when it's exposed to light. And so now all of the paintings in which Van Gogh used eosin, and unfortunately a lot of his works involve the use of this geranium lake, now have a very different appearance than his original intent. And unfortunately the pink tone that you see in the floor is also due to eosin, and so that is changing color as well. And so here's a look at the eosin molecule, and again, here is a cross-section of the paint layers in the floor, and you can see some of the individual red eosin pigment particles that have not yet faded. But this cross-section was taken because, as you can see, the floor is starting to change color, just like the walls change color as well. And so the amount of light exposure that this painting gets is going to be critical for its long-term survival. But we're going to focus on the chrome yellow paint that he used in the bed frame here. Okay, so if we look at a cross-section of the chrome yellow paint, at the bottom everything looks really good. We have the bright lemony yellow color that we would expect, but at the top things really are not looking so good. We have these dark brown crystals forming. So in terms of what's causing the darkening of the yellow pigment, it turns out that it's light-induced chemical reactions. And the reason we know this is that we've been able to reproduce the phenomenon using a technique called artificial aging, essentially ultraviolet light exposure over a short period of time. And so here are samples that my colleagues made of unaged chrome yellow, and then after it's photo-aged, you can see that it's starting to turn brown on the surface, just like we see in the Van Gogh. And unfortunately, that dark surface on the painting is very, very thin. And so the scale bar here is 200 microns, and to give you a way to sort of relate to that number, Human hair, depending upon what part of the world you're from, varies between 50 and 100 microns. And the thickness of this darkened layer of the yellow paint is only about 3 microns or so. And so we have very little material to deal with in terms of the material we need to analyze. And so what we're looking at here is a very large piece of cake, but also a huge experimental challenge, because we need to do molecular analysis as a function of depth into the paint layer, and we need to use that information in order to identify the degradation mechanism. And then also, once we identify the degradation mechanism, then we can determine the safe display conditions for the painting. So here's what the molecular analysis of the paint layer looks like as a function of depth. So we're looking at depth into the painting in this direction, and what we see happening is the light-induced reactivity of the chromium in the chrome yellow. And so the chromium is actually gaining electrons when it's exposed to light. So inside the chrome yellow pigment, which is a lead chromate, we have chromium 6+. So in the center of the paint layer here, we have chromium 6+, but on the surface, we have chromium 3+. So what we call the oxidation state has changed. So why does it matter that the oxidation state has changed on the surface? Well, remember that chrome yellow is actually this nice, bright, lemony yellow color, but it turns out that when chromium 6+ changes to chromium 3+, then a new chromium compound is formed, which is also an artist's pigment. It's a green pigment called viridian, and that's what's shown here. But then we also have chromium sulfates and chromium acetates forming, and these are shown here. When you mix all these compounds together, unfortunately, you get a dark, muddy brown color, and that's what we're seeing on the surface of the painting. So how would one go about identifying all of these compounds? Because that's really the first step in preserving these priceless works for the future. And it turns out that we have to use a synchrotron, just like the one here at SLAC. And inside a synchrotron, electrons are going to be accelerated to nearly the speed of light, and we're going to have very intense X-ray beams being given off tangentially to the ring containing the electrons. And when I say a very intense X-ray beam, I mean somewhere between 500,000 and 1,000,000 times more intense than the X-ray beam you would be exposed to, for example, if you had your arm X-rayed at the doctor's office. And the reason that we like these very intense X-ray beams so much for studying art is that they give us elemental analysis information using a technique called X-ray fluorescence, and they also give us molecular analysis information using a technique called X-ray absorption near edge structure. And so these are two of the synchrotrons that we used in our research, the one here at SLAC and then also one in Grenoble in the south of France. So this is X-ray absorption near edge structure that was used to study the Van Gogh, and essentially it's a molecular fingerprinting technique. In terms of why it works, different chromium compounds are going to absorb X-rays differently, and we can use that feature in order to identify them. And what happens is that when a compound absorbs X-ray energy, so we're looking at increasing X-ray energy in this direction, there's going to be these spikes in absorption when the atom in the compound is ionized, or when an electron is kicked out from that atom. And these spikes in absorption have certain characteristic features for different chromium compounds, and so you can see these little wiggles after the spike in absorption called the absorption edge for chromium 3+, and you can see this strong peak before the absorption edge for chromium 6+. And so even just looking at these two plots without really knowing what the wiggles and the spikes mean, there's no way that you would confuse one for the other. They're very characteristic of the different chromium compounds. And here are the results of the Zanes analysis of the Van Gogh, and the analysis spot is shown here in this little oval in the brown area. And it turns out that it's about an equal mixture of chrome yellow, of viridian green, and chromium sulfate, which when mixed together are forming this dark brown color. And so now that the degradation mechanism for this work is understood, a preservation strategy can start to be developed to preserve it for future generations. The second example that I want to take a look at involves zinc yellow, or zinc chromate, and perhaps the greatest masterpiece from the Art Institute of Chicago, George Seurat's A Sunday on the Grand Jatte. And this painting was painted over a fairly long period of time, between 1884 and 1889, and you can imagine why when you think about putting all of those individual dots on the canvas. So really what we're looking at here is just an exceptional pointillist or divisionist masterpiece. And unfortunately, if you look very closely at this painting, right at the interface from where the grass is in shadow to where it's in sunlight, this is what you see, that what was originally a very bright yellow pigment, and look at what it looks like now, it's kind of this ugly ochre brown color, and then the green points were made with the emerald green, and you can see how it's turned this unpleasant olive color. And so there's really been some dramatic shifts in this work over time. But what's quite astounding is that even by 1892, people were starting to notice this, and critics were saying that the painting's colors had changed dramatically and that the painting had lost some of its luminous charm. And so people think that a lot of these degradation problems are happening over hundreds of years, but some of them can happen even over a matter of several months or just 1 or 2 years. And what I've put here is a list of all of the different light-sensitive pigments that were used in creating this single painting. And so really, protecting this painting from light is going to be critical in terms of preserving it for future generations. And if we look at a cross-section of the zinc yellow paint, you can see that same phenomenon of a brown crust, very thin, just a couple microns forming on the surface. So in terms of understanding why the zinc yellow is changing color, a technique called eels was used in order to find out. And you might think, okay, I'm feeling good. I know what an eel is, but in fact, this is not the eel we're going to talk about. We're going to talk about electron energy loss spectroscopy. And the way that this technique works is that you remove a tiny sample from the painting and hit it with a high energy electron beam. And the electron beam loses a very small amount of energy when that happens. And the amount of energy lost by the electron beam is characteristic not only of what atoms are present, but what their oxidation states are. And if we look at the EELS data of the top surface of the paint, which is brown, versus the undersurface, which is yellow, what you can see is that there's been a shift in the spectra. So the top surface is shifted a little bit the spectrum is shifted a little bit over to the left versus the spectrum for the bottom surface. And what this means is just what we had seen for the Van Gogh, that there's chromium 3+ on the top surface and chromium 6+, the dichromate that we should have on the bottom surface. And so again, we're having a light-induced change in chromium's electronic state, and that's what's causing the alteration of the colors in this particular painting. And so again, once we understand the technology involved in the paint changing color, we can start to formulate a preservation strategy. Okay, the next work I want to talk about is Edvard Munch's The Scream, and look at the degradation of cadmium yellow. So it turns out there's several different versions of The Scream, and the one I want to focus on is the 1910 version from the Munch Museum that was recently stolen and then returned after a couple years. And you can see the water damage as a result of the robbery here and over into here as well. But I'm actually going to focus on a different type of damage in this painting. This is a brushstroke that was originally a bright yellow and has now faded away to a white color. And so it is important for these paintings to think, what are they going to look like 50 years from now? And what might they look like 100 years from now? It's really quite terrifying. And in fact, I was so excited. This is the first time that I've ever given a lecture when I came into the auditorium and they handed me a prop showing 200 years from now what this painting is going to look like. So I was very grateful for that present from SLAC. So a lot of people ask me what it's like to work in this field when you're handling not only icons in terms of our global cultural heritage, but icons that are very specific to certain countries. And certainly the scream is not only an icon of a mental state, it's also an icon for all of Norway. And the only thing I can tell you about working with these types of precious works of art is that it's absolutely terrifying. And when we arrived in the Oslo airport and Apurva and I were heading up the escalator, this is what greeted us at the top of the escalator, and we thought, oh my God, we're really doing it. And the scream is literally everywhere you go in Oslo. And so not only is the scream a national treasure for Norway, but it also is very intimately associated with Oslo, because of course what you're looking at is a scene of one of the fjords in Oslo. And I had to put another pastry in here. So I was very honored to be able to work with some of our Scandinavian colleagues. This is Un Plater, who was showing us where the fading has taken place in the sky and also in the water, where there's been a lot of paint loss in the cadmium yellows as well. And when we worked on the painting this summer, we were able to use the characteristic fluorescence of cadmium yellow in the infrared to identify where it was in the painting. And then we also did elemental analysis of all the different paints using a technique called X-ray fluorescence. And so essentially what we were doing was exciting the painting with ultraviolet light, with relatively high energy light, and then looking at the light emitted by the cadmium yellow, which was lower in energy in the infrared. And we had a special sensor on our camera that enabled us to see the infrared fluorescence that indicated that this was a cadmium yellow brushstroke. This is another cadmium yellow brushstroke here. And so when you have fluorescence like this, you're really looking at a two-step phenomenon, where the first step is light being absorbed, and the second step is light being emitted or given off at a longer wavelength. And similarly with X-ray fluorescence, we're hitting the painting with a high energy beam of X-rays, and we're looking at the energies of the X-rays that are then emitted by the pigments in the painting. And the energies of the X-rays coming off of the painting are characteristic of the different elements that are present, and therefore from that we can infer the different pigments that are present. This was perhaps one of the most terrifying moments of working on the screen, realizing that in order to get all the data we needed, that we had to change the orientation of the work. But fortunately, we had Apurva Mehta from SLAC overseeing the whole thing and telling us that it would be much easier to analyze the painting if it was on a diagonal than straight up. That's a joke. So it turns out that when we think of the scream, often we think of one painting, but the scream is actually 4 different paintings. There is the one at the National Museum in Oslo, and that's in excellent condition, that's shown here. And the one that we are currently focused on is the Munch Museum version from around 1910, but then Munch also did 2 different versions in pastel as well. The 1895 version you might have seen in the news recently, because last year it sold at Sotheby's for $120 million. And so when we think about having research access to this painting, we can think about it being going, and gone, unfortunately. But we do have these other 3 versions that we can study closely. So the scream was painted by Munch in the context of a series of paintings that he called The Frieze of Life, which he called a poem about life, love, and death. And it starts off with this incredibly cheery painting here called Death in the Sick Room. And so I'd like to propose that the true title of The Frieze of Life is actually really more like a poem about love and death. And I'll show you a couple of other examples of his work. We have Ashes, An Evening on Karl Johan Street, and people have pointed out the tension and anxiety and sorrow that they see in the faces of the people in this street scene. And then finally, Munch just cuts to the chase and says, okay, I'm going to call the painting Anxiety. And this is essentially what we feel like in art conservation, knowing that his paintings are changing color and that it's up to us to figure out what to do about it. So now I'm going to switch to a much happier painting. This painting is actually called The Joy of Life, and it was done by Matisse in the winter of 1905 to 1906. During this time, he was receiving very little critical recognition, and in fact, he was receiving an awful lot of scorn for his work, and so he didn't have very much money. And in fact, in a 1925 interview, he even talks about his financial circumstances during the time in which he made this painting, and he said, and this is critical for an artist, "We didn't even have enough money to buy a beer." So things are really bad. And then he goes on to say that we didn't have money to buy colors, especially the cadmiums, which were expensive. And this is critical because if we look at the size of the painting, for those of you that haven't been to the Barnes Foundation, it's monumental. This painting is nearly 8 feet across. And so you can imagine he's having financial difficulties trying to come up with the expensive paints for this entire work would have been quite challenging. This painting has been at the Barnes Foundation in Philadelphia since 1922, and it's considered one of the great icons of early modern art, and unfortunately, its condition is rather grave. It's undergone extensive discoloration, particularly in this region under the central reclining figures. And this has been an international collaboration that's been going on for several years. It's been very challenging to untangle the chemistry in terms of what exactly is happening with the pigments changing in this painting. But what's been really helpful is just like the Scream, there's actually 4 different versions of The Joy of Life, which I'm showing you here. So in addition to the monumental Barnes version, there's also a version in Copenhagen and here in San Francisco, which is one of the reasons that I'm in San Francisco this week to study this 4th version. And so if you compare the San Francisco version and the Copenhagen version to the Philadelphia version, what you can see is this warm yellow in the upper left corner is now this sort of tan brown color, and that underneath the central reclining figures, what was a nice light bright yellow has now faded away to an ivory color. And unfortunately, the paint is not just changing color, it's also flaking off after the color change happens. So we have 2 different works, The Scream and The Joy of Life, that are both fading at where their cadmium yellow paints are being used. So the question is, what is happening to these 2 works? And what's important to know in order to answer that question is that cadmium yellow during the turn of the 20th century was typically an impure mixture. And the reason for this is that white materials were added to the cadmium yellow to make the paler shades of cadmium yellow. And so cadmium sulfide yellow by itself is actually really dark. It's almost an egg yolk color. And so the paint sellers would add cadmium carbonate or cadmium oxalate to it in order to make the lighter shades of cadmium yellow. And it turns out that the cadmium yellow paints from the turn of the 20th century were also contaminated, and this contamination was actually leftover materials from their manufacture. Typically, cadmium yellow would be prepared with either cadmium sulfate or cadmium carbonate, both of which were white compounds. And the reason why it's so important to know about all these impurities is that all of these compounds also form when cadmium yellow fades over time. And so when the white compounds are present throughout the paint layer, when they're evenly dispersed, like I've shown here, then they're likely fillers and starting materials. On the other hand, if the white compounds are present at the top of the paint layer, then they're likely due to photodegradation or degradation due to exposure to light. So in the case of cadmium yellow, we see it changing chemically as a result of oxidation or losing electrons. And specifically, it's the sulfur that starts off at 2- and loses 8 electrons to become sulfur 6+. And when that happens, the cadmium sulfide is converted to white cadmium sulfate. And so you can get this type of layered structure. And so it's critical not only to identify the presence of cadmium sulfate, carbonate, and oxalate in these paints that are changing color, but we also need to know the spatial distribution of these compounds as well. So if we look at the condition of The Joy of Life, there's 3 major problem areas. There's the area that's turning brown in the upper left corner, and then there's this kind of tan film that's forming over on top of the fruits in the tree. And then there's the ivory color forming underneath the central reclining figures as the yellow fades away. And we're saying that the high impasto areas are flaking away. High impasto is thickly applied paint. So if you think of icing a cake and you're making these peaks in the icing, artists would do the same thing when they painted. And those peaks are heavy and will fall off when the paint starts to degrade. And in the case of the Scream, we have the brushstroke that's turned white in the sky, and this is a digital reproduction of what the color would actually have looked like. And also in the water, we have this area where the cadmium yellow is flaking away. And during the work we did this summer, we found out that there were actually cadmium yellow brushstrokes in the main figure's neck as well that have now turned white. So when we do elemental analysis of this paint, it turns out that we have the wrong ratio of cadmium to sulfur in the paints that are fading or darkening. And so I did this experiment just by going to the art supply store and buying a tube of cadmium yellow paint. And we should expect a 1-to-1 ratio of cadmium to sulfur, and that's essentially what we see in the brand new tube of cadmium yellow. And it's also what we see in the National Museum Scream that's in such good condition. But if we look at the Munch Museum Scream, you can see that there's very little sulfur left. And if we look at the Joy of Life, there's almost no sulfur left at all. So what does this mean? It means that the cadmium yellow is impure, and there's really 3 possibilities in terms of what could be going on. The first is that we're looking at leftover production materials. So there's cadmium sulfate or cadmium carbonate that's present in the paint as a result of how the paint was produced. The second possibility is that we're looking at fillers that the paint manufacturer added to the paint, such as cadmium carbonate or cadmium oxalate. And then the third possibility is that the paint is filled with cadmium oxalates, carbonates, and sulfates as a result of photodegradation. So how do we tell the difference between these 3 different possibilities? Well, we really have to look at where these different compounds are located within the paint layer. And so before we did that, we went on and did molecular analysis of the paintings using a technique called infrared spectroscopy. This is a molecular fingerprinting technique where we're using the patterns of molecular vibrations in order to identify the different compounds that are present. And it turns out that in both the Joy of Life and the Scream, we see high concentrations of cadmium carbonate, and the green spots here are pointing out the peaks for cadmium carbonate. So then we went on to study the faded paint under the central reclining figures here at SLAC, and what we found out was that the overall composition was less than 15% cadmium sulfide. So the cadmium sulfide has almost completely gone away under the central figures, and that the paint is now largely made up of cadmium carbonate and cadmium sulfate. Well, cadmium carbonate and cadmium sulfate are both white, so that would certainly explain why the paint was fading. But again, we need to demonstrate that they're forming at the surface of the paint layer. And we further went on to identify sulfates in the Joy of Life using that same molecular fingerprinting technique that involves using molecular vibrations. And we also have started to see our first hints that there might also be sulfates present in the Scream as well. And this is important because it points to the direct change of cadmium sulfide to cadmium sulfate. And then here's a look at a tiny flake of paint that we removed from one of the yellow fruits in the tree of the Joy of Life. And you can see that there is a white degradation crust forming on the surface of an actually very intact bright yellow paint. And when we look at this same paint cross-section in ultraviolet light, it has this characteristic crazy orange fluorescence that you see for cadmium yellow as it starts to degrade. We can also do an elemental map of the faded paint, sort of like X-ray fluorescence on a microscale, and each of the green data points here represents a sulfur data point, and each of the red data points represents the presence of cadmium. And you can see that cadmium is present throughout the paint layer, but that sulfur is being lost at the surface of the paint layer. Also in the electron microscope, we can see the physical breakdown of the paint layer as well. So you can see all these cracks running through the paint. The paint is actually starting to crumble. So we have a chemical change, the loss of sulfur, and then a physical change as well. And it's thought that this physical change, this crumbling, is a result of acid attack on the oil binding medium that's related to the formation of sulfates when the cadmium sulfide converts to cadmium sulfate. And macroscopically, unfortunately, this is visible in the painting. The paint layer becomes very dry and chalky, and then ultimately it starts to flake off when this happens. And we can even see, if we map the oxygen content of this region of the paint layer, that we have quite literally an oxidation. Oxygen is shown in blue here. And so oxygen is essentially replacing sulfur in this region of the paint layer where it's fading to white. And we took another sample to the synchrotron, and we looked at the molecular composition of the paint cross-section as a function of depth using Zanes. And what you can see is that in the white degradation crust on the surface of the paint, the cadmium sulfide is completely gone now. All we have left is cadmium carbonate and cadmium sulfate, which again explains why it's white. But now, if you look at how much cadmium carbonate is in the surface, 91% in one area. And so it looks like cadmium carbonate really is a degradation product here. It's not something that was added by the paint manufacturer. And it's more difficult to interpret the cadmium sulfate data because that's actually present throughout the entire paint layer, but we think that's a function of the high solubility of the cadmium sulfate. And then we also used a synchrotron to do molecular mapping of this particular paint sample, which comes from underneath the central reclining figures. So this is the paint sample in visible light. This is the sample in ultraviolet light. And we took just a very thin slice off the front of this paint sample and then squashed it out flat so that it would be or infrared radiation could be transmitted through it. And we were able to get a molecular map of this little slice of the paint cross-section. And what you can see is that oxalates are concentrated in the white photodegraded layer. And so the oxalates are also a photodegradation product as well. They're not something that was added by the paint manufacturer. And we see the carbonates showing up below the oxalates, and then the sulfates again distributed throughout the entire paint layer. So what about the role of cadmium carbonate in the screen? How are we going to recognize when cadmium carbonate is actually present as leftover material from the production of the pigment? Well, it turns out that cadmium carbonate is a highly insoluble material, and so when it's used in order to make the yellow cadmium sulfide, the cadmium sulfide actually forms on the surface of the cadmium carbonate. And this is a phenomenon that we've been able to witness in another Matisse from the Barnes Foundation, this one called Flowers in a Pitcher. And in this case, we were sampling not the yellow that's turned brown over time, but this lemony yellow that's in very good condition. And what we're looking at here is elemental and molecular maps for this lemon yellow sample. And what we're looking at here, all of the hot spots in this map are the different cadmium-containing pigment particles. And the real exciting information is that if we map out cadmium sulfide and cadmium carbonate, you can see that they're highly correlated. And this suggests that these materials were precipitated or they came out of solution together. There's really a one-to-one correspondence. Wherever you see cadmium sulfide, you also see cadmium carbonate. And that suggests this structure for the pigment particles. And so really what we're looking for in terms of trying to identify if cadmium carbonate is a leftover starting material or if it's a photodegradation product is this type of microstructure in the paint versus this type of microstructure in the paint. And so finding cadmium carbonate in the screen is not enough to tell us what the mechanism of degradation is that is happening in the screen. We really need to go on and do further analysis, for example, definitively finding out whether cadmium sulfide is present, and also finding out if any cadmium carbonate is collecting up at the surface of the paint layer. And we just got the samples necessary to do that in Oslo this summer. So in terms of where we are now, in the case of The Joy of Life, we're trying to assist with the art historical reinterpretation of the work. Unfortunately, many art historians over the last century have been interpreting not Matisse's original intent, but some of the changes that have happened over time. And so in 2004, you have an art historian saying, the dirty yellow ground is for the most part patchily scrubbed in, and that was definitely not Matisse's original intent. And so we really have to go back and reevaluate some of the scholarship that's been done on this work. And of course, the research that we've done is leading to better preservation of this work for future generations. And so the Barnes Foundation just recently moved into Philadelphia, and the Joy of Life is still being shown. It will probably always be on display. It's such an important painting, but now with substantially lowered light levels and with highly stabilized levels of relative humidity. And in the case of the Scream, further study is necessary to fully understand the degradation mechanisms that are going on in the case of this work. So one of the things that people have asked about these paintings is, can the damage be reversed? That's something that would be really quite challenging because the sulfur is actually lost from the paint. That's what we found out when we did the analysis of The Joy of Life. And you can see we've got all kinds of cadmium present, but the sulfur is almost gone. And so it's more common in our field to do essentially a Photoshop reproduction of what the work would have looked like originally. And in the case of The Joy of Life, we have, of course, the Copenhagen version and the San Francisco version that are still in extremely good condition. And it is possible chemically to think about taking the cadmium sulfate and converting it back into the cadmium sulfide in principle, but you really don't want to do this chemistry on such an iconic and priceless work of art. So that's something that we would definitely try in the lab first before we thought about ever doing it on a real painting. And then another question we commonly get asked about this work is this going to happen to my painting if you're using cadmium yellow, chrome yellow, or zinc yellow in your paintings now? And the answer is no. That the way these pigments are made currently, a lot of the problems with the manufacture have all been worked out. And so it's not something that we see in modern paintings, although modern paintings have a whole host of other degradation issues associated with them. Okay, so all of this research is still very much ongoing and keeping us out of trouble now that we have the San Francisco version to study at the end of this week, and the research on the Scream is really just getting started. And so I'm very grateful to have had the opportunity to speak with you a little bit about this research. And so I'd like to thank you for your attention, thank the many people who funded this research and participated in this research as well, and I'm happy to answer any questions.